Okay, it's time. I think so we can start our webinar today. Good afternoon and Assalamu alaikum. Dr. Pieter Boom is there with us and the attendees for this webinar today. It is our second webinar for IRC-CBM in this year, 2022. And today we have speaker from one of our affiliates from Mechanical Engineering Department, Dr. Pieter Boom, who has recently joined our center as an affiliate. And we have an interesting topic. Our subject area to be addressed today is modeling, which is one of the themes of the webinar of our IRC-CBM. So you can see over here in our themes on the left side, you see that modeling is one of our principal theme in this center. So we have an interesting presentation today on discrete exterior calculus for non-smooth solid mechanics on supercomputer. And this webinar is facilitated by KICS, and it aims to provide a platform both for KFUPM and community outside to get up-to-date information about the webinars. Throughout this presentation, all attendees will be muted, and you can type in your question in the question box, which will be taken up at the end of the presentation. And also, after the webinar, there will be a survey form which will be given to you via email. So please let us know how you feel about this webinar and what we can address in our future webinars. So let's start by introducing our speaker today. Our speaker today is Dr. Pieter Boom. He is an assistant professor in Mechanical Engineering Department at KFUPM and is affiliated with the Interdisciplinary Research Center for Construction and Building Materials. His research interests lie in development of robust and efficient numerical methods for massively parallel engineering simulation on non-smooth multi-physics physical phenomena. Dr. Boom earned his PhD in aerospace science and engineering from University of Toronto in Canada in 2015, and his dissertation focused on the generalization of summation by parts finite difference operators and optimization of high-order implicit time marching methods for unsteady computational fluid dynamics. He was then appointed as postdoctoral fellow on an Airbus-funded project at the University of Toronto, 2014 to 2018, investigating the use of synthetic jests for turbulent boundary layer drag reduction. Finally, prior to joining KFUPM in January 2022, Dr. Boom worked as a postdoctoral research associate on an UKRI EPS RC fellowship and was an investigator on an Archer 2 UK National Supercomputing Service Grant at the University of Manchester from 2018 to 2022. In this role, he was first to fully describe linear elasticity and thermal diffusion in media with evolving discontinuities using discrete exterior calculus. He also developed a parallelized software library implementing DEC with excellent scaling on over 10K processor. So let's welcome our speaker, Dr. Pieter Boom. And Dr. Pieter Boom, you can, I'll stop sharing and you can unmute yourself and start sharing the slides.
Okay, thank you very much for that kind introduction. Assalamu alaikum, everybody. Did we lose our slides?
Yes.
Oh,
it can't. Yeah, now.
Okay, thank you. So assalamu alaikum, everybody. Thank you for giving me this opportunity to share some of the work that I've been doing recently. I say the work that I've been doing recently, but I can't take credit for all of it. As you can see at the bottom of the slide, I have a fair number of collaborators at the University of Manchester. I've also been working with people throughout the UK and the US and further abroad as well. So this is kind of a summary of a lot of people's efforts. And so hopefully you find it interesting. So the basic motivation for this work is that we want to engineer and design large infrastructure that has a long service life. It's not like an iPhone where in 2-3 years you get a new one. We expect that these facilities to be in operation for decades. And these are critical both to our society and to our economy, providing, for example, power or transportation or places to live. And so we want to have an accurate way of determining how these structures will evolve as they begin to age, as they incur damage, and heaven forbid if they ever fail. So we need numerical tools that are able to help us predict these phenomena. Failure to accurately predict this behavior often leads to over-engineering or early replacement of components, unexpected failures, and this can cause injury or loss of life, as well as costing the global economy billions of real every year. So the challenge is that these phenomena are often non-smooth processes. So either they involve some discrete phenomena, are heterogeneous, or discontinuous. And if we take the materials that we're interested in using and we zoom in to the mesoscale, so this is above the atomic scale, but above the continuum scale, we see that there are a lot of discrete structures in materials, whether it's a polycrystalline material, whether it's a concrete with aggregates, whether it's a fiber reinforced plastic or concrete, whether we're dealing with mechanical metamaterials, we see that there are a lot of discrete structures. So if we think about the traditional way of modeling these structures and their behavior, at least at the engineering scale, we often use continuum models. And by definition, these models can't accurately predict the performance of these materials and their structure at a fundamental level. Now, granted, we're getting very good at developing models. However, if we're interested in the fundamental phenomena themselves, then we need a more closely related numerical description that allows us to investigate these problems. So the goal of my research is to develop fundamentally discrete descriptions of non-smooth material processes. So we're interested in materials that have some form of structure or discreteness to them, structures or materials that have spatial variability. We're interested in heterogeneity and discontinuities. We're interested, this is my term, I call it simultaneous multidimensional processes. But the idea here is, for example, imagine that you have a 3-dimensional matrix, and within that matrix, you might have platelets. So this could be, for example, graphene nanoplatelets or something, which, while in reality have a finite thickness to them, we can essentially, or we would like to essentially treat them as 2-dimensional. Or if we have carbon nanotubes, we want to treat them as essentially 1-dimensional. So how can we have a 3-dimensional problem where we have processes evolving in 1 dimension or 2 dimensions or in multiple dimensions simultaneously? So you could think about something like hydrogen diffusion in a polycrystalline material, for example, where you might expect different rates of diffusion through a grain as opposed to along a grain boundary. And so we can model these within the same numerical tool at the same time. I'm also interested in multi-physics processes and multi-scale processes. So how can we apply these methodologies from the mesoscale and access some things from the microscale? So can we also access or interface with atomic scale modeling, and how do we scale this up to engineering scale problems as well? And so in this presentation, I'm going to focus on discrete exterior calculus, but in general, interested in the application of discrete forms of exterior calculus implemented in high performance computing software so that we can solve these large scale engineering scale simulation problems. So I'm going to give a very brief introduction to exterior calculus. It's quite technical, it's quite mathematical. So I will go through this relatively quickly, and if you have questions, I'm happy to talk more about it at the end. This work was initially came out of a group at Caltech in the early 2000s. One of the seminal papers was actually a PhD dissertation by Anil Hirani. I believe it was in somewhere between 2003, 2005. So this is not my own work. This is developed by a number of applied mathematicians. It's been applied in computer graphics. It's been applied in modeling of electricity magnetism, incompressible fluids for planetary flows. I believe there's a group at KAUST that's working at that. This is a mathematical concept that's been applied in a variety of different contexts. But here we're going to be looking at it in terms of modeling materials. Okay, so at a very high level, we're interested in calculus. So we're interested in describing change, and we want to do this through integration and differentiation. So adding things together and then looking at rates of change. So we're probably very familiar with vector calculus, which is concerned with continuous fields, scalar fields, vector fields, tensor fields, evolving in 3D Euclidean space. We can then generalize these ideas to what is called exterior calculus. Exterior calculus has been around nearly as long, if not as long, as vector calculus. It's maybe a little bit less well known, but the idea is to generalize this analysis to differential manifolds in arbitrary dimensions. The last step, or the last piece of the puzzle, is to take these ideas and then extend it further to piecewise flat manifolds. So here we have an example of a cylinder that has been approximated with a piecewise flat manifold, and we're specifically interested in oriented manifolds. And we'll talk about this a little bit more in a minute and why it's important. And for the purpose of discrete exterior calculus, which is one discrete form of exterior calculus, it focuses on the use of simplicial complexes and their Voronoi duals. And we'll go through this a little bit more in a minute. So I'd really like to highlight at this point that our use of discrete exterior calculus is very different to the way you might use finite elements or finite differences or finite volumes. The idea here is not to discretize a continuous field, to start with a governing equation that's continuous and then to represent it as in discrete pieces that we add together or we study their interaction, but rather to define the behavior of the physics itself on these discrete pieces, these discrete entities, and then to describe the physics through the geometry of these discrete pieces and how they interact with one another, which is the topology of the mesh. So as I said, we're interested in simplicial complexes for discrete exterior calculus. This is going to define what is our primal complex. So here we've started with wanting to model a cylinder, and we've approximated it with a simplicial complex. But the long-term goal is that we take a material microstructure. So whether this comes from tomography or wherever we get a microstructure, and that the cells that we use to model this are that microstructure. So here we're approximating a cylinder, but in the end, we actually want to deal with that microstructure as our base cell. So it's possible that we can also use the Voronoi dual as our base discretization to get a little bit more geometric freedom. One of the really interesting and important aspects of this theory is that we deal with the geometric orders separately. So you might have a finite element that has a boundary and you want to compute a flux through that bounding face. But here we apply that same idea. We still have that, a k-dimensional cell has a boundary that is a k-1 cell. But we can actually define physics separately on our 3-dimensional cell, on our 2-dimensional cell, on our 1-dimensional cell. And we can have the physics evolving differently. We can also assign different material properties to each of these dimensions and their interactions separately as well. We also want that these cells, whatever dimension they are in, to have an orientation. So we start by taking our top dimensional cell. Here, it's a 2D example where we want those cells to induce an orientation at their boundary, at their interface, which is equal and opposite from one side to the other. So you can see that on one side, the induced orientation in the 1, 3, 2 cell is up and to the left, and in the 1, 2, 0 cell, it's down and to the right. And what that means is if we have homogeneous properties between our cells, that this interface essentially disappears, and we can treat it as one cell. Now, if the properties in either cell is different, then it may not cancel exactly, and through that process, we can introduce discreteness. But this is a way that we can recover continuous solutions if we so desire and need to. So we want to look at how we can do integration with discrete exterior calculus. And the way that we do this with our discrete elements is we define two mathematical objects, the first one being K chains and the second one being K cochains. The idea behind a chain in this formulation is that it's essentially interpreted as an oriented indicator of our domain of integration. So you can imagine that we assign to every cell, whether that's a 3 cell, whether that's a face or an edge, an oriented indicator. So if it's 0, we're assuming that we're not including that cell in our domain of integration. If it's 1, it is included. We can also introduce multiplicity in our integration, or we can say that we want to integrate certain cells with an opposite orientation by adding a negative coefficient. Now, in contrast or in complement to K-chains, we have cochains, which is assignment of a scalar to each simplex in our overall complex. And we're interpreting this as a linear functional. Now, this linear functional is defined implicitly with respect to the geometry of that cell that it's defined on, so that when we want to do integration, we just have the product of chains and cochains. And this is how we can do integration on our complex. Now, we also want to be able to do differentiation. And the relationship between integration and differentiation is through Stoke's theorem. So we've all come across this in one form or another. Basically, the idea is that if we want to have a function integrated over the boundary of an oriented manifold, then this is equal to the differential of that function integrated over the entire manifold. So this, in one dimensional, we've all seen this in the fundamental theorem of calculus in one dimension, that if you want to integrate a derivative over an entire domain, it's equal to that function evaluated at its boundaries. It's the same idea. So here we then define the discrete exterior derivative, which is a linear map from K-1 cochains to K cochains. So the idea being that we're moving from something that exists on a boundary to something that exists on the interior of a K cell, right? Very similar to the definition of Stoke's theorem. And fortunately for us, in discrete exterior calculus, these are very sparse matrices that are either 0, 1, or -1, depending on their connectivity and the orientation of adjacent cells. Also, we observe here that there's no inclusion of the metric of the space. So it's very basic, but we will see other operators which introduce the metric and help us to recover some of the things that we might be expecting. So this here, the definition of our discrete exterior derivative gives us a map from K-1 to K, but where we might also be interested in moving in the other direction from K cochains to K-1 cochains. So how do we do that? And the way that we're going to do that is through a dual complex. So here the idea is to have a second mesh, whether it's defined explicitly or only implicitly, where each dual K cell is associated one-to-one with a D-1 simplex. So D being the dimension of our space. So here we can see that the geometric order of the primal and dual move in opposite directions. Therefore, when we apply a discrete exterior derivative in our dual complex from D the space of all K-1 cochains in the dual complex to the space of all K cochains in the dual complex, that we're moving essentially in the opposite direction in the primal complex. What remains is to have a map between our primal and dual complexes. This is done through a discrete Hodge star, and for the purpose of discrete exterior calculus, these are diagonal maps diagonal matrices, if you're dealing with matrix form, that are a map from either the space of all k cochains in the primal to the space of all dual cochains, d minus k cochains, or the other way around. And here we introduce the metric of the space. So if we put all of these pieces together, we get a Theorem complex, which is something that you may have seen in other methods. And we have our discrete exterior derivatives, our d and our d stars, which would be the exterior derivative in the dual, which in our case ends up just being the transpose of the exterior derivative in the primal. And we have our Hodge stars, which relate our dual and our primal complexes. Now, this is nice. We now have a framework where we can define our physics in a completely discrete world. But the reality is, and one of the challenges that we've faced in solid mechanics is we've spent so many times relating things to continuous descriptions that we often want a way of relating what's happening in our discrete complex to what's happening in our traditional continuum descriptions, whether that's to impose boundary conditions or to extract things like stresses, which is a continuum concept. And so we also need something called discrete musical isomorphisms, which if you think in terms of tensors is an index raising or lowering operation, where we can create, at least in the discrete context, approximate maps between vector fields and our cochains in our discrete complexes. So a flat will take an approximation of a map from vector fields to our cochains, and the sharp operation is the inverse, taking information on our cochains and mapping it back to an approximation of our fields. So overall, we have a map between continuous scalar, vector, and tensor fields and our discrete complex. And this allows us to at least mimic operations like gradient, divergence, and curl, and then combine them to build up more complex operators such as the Laplacian. Okay, so this has been a very, very quick introduction to discrete exterior calculus. Again, if you're interested in more of the details, we can talk about it in the Q&A afterwards. But this is basically our mathematical framework for now developing our solid mechanics. So before we get into mechanical properties, we'll just take a step back and look at a class of elliptical problems. So this could be used to describe Fourier's law, Fick's law, Ohm's law, Darcy's law. Here, as an example, we're going to consider Fourier's law for heat flow, heat diffusion. We're going to look at it at steady state. However, the numerical tools that we've developed, and I'll talk about in a little while, have time integration implemented in them, so we can look at time-dependent problems as well. But for now, we're just going to look at steady state problems. So here, our conservation ends up being the divergence of the heat flux through each of, well, this is the divergence of the heat flux. So we're defining this in the continuous case over a domain M in three-dimensional space. And then our fluxes are defined as the negative gradient of temperature times our thermal diffusion, our thermal conductivity coefficient. We then want to also imply both the Dirichlet and Neumann boundary conditions. The Dirichlet boundary conditions for temperature and our Neumann boundary conditions for our fluxes. So we now want to write this in terms of our discrete formulation. So we are going to apply a flat discrete musical isomorphism. And so our temperature becomes a zero cochain. So if you think of the primal description of our material being dual 3 cells, so there are Voronoi cells in 3 dimensions, then our temperature is defined at a primal cell, which will be at the center of that dual cell. And then the flat of our fluxes, we're going to call omega, and is going to be a dual cochain, dual 2 cochain, which will be the boundaries of that dual 3 cell that we're interested in evaluating. Okay, so we can now take the discrete exterior derivatives that we've defined in our Hodge stars, and we can now apply it with these musical isomorphisms to rewrite our Fourier's law. So here in our first line, we have D0 transpose applied to our discrete flux. So this behaves as a divergence of our fluxes. And the Hodge star is would be star zero inverse, which allows us to go back to the same points where we've defined our primary unknown, our temperature. In terms of the flux itself, we can have a relationship between the flux and the temperature. Here, D0 represents a gradient, a discrete gradient of our temperature, and then our star 1 sub kappa gives us both the isomorphism from a 1 cochain to a dual 2 cochain, but also includes our material properties. So that would be our thermal conductivity. Okay, and so what we've done here is we've taken a continuous description and we've rewritten it in a discrete context, which is what I said earlier, what we don't want to do. But bear with me for a minute. We can apply this to a continuum description as you might do a finite element method, and lo and behold, we can recover the exact solution. Here it's for a linear problem where we've applied a pressure or a thermal difference, a temperature difference from the top and bottom surface, and then we've calculated our Fourier's law in our cube and in our deformed cube here, and we get the analytic solution to within machine precision. It does look a little bit blocky because the coloring is constant within each cell. But if you evaluate it at the cell centers, we do get back the analytic solution to machine precision. The interesting thing is when we do this with discrete exterior calculus is that we can start introducing discontinuities. So if you look on the figure on the left, you should be able to see that we've introduced a small discontinuity. So this is a face that we've assumed is essentially like a crack, if you want to think of it in terms of material, and we can calculate how the temperature, the heat flows around that discontinuity, which is something that if you want to only introduce one discontinuity, you can do with finite elements. But what discrete exterior calculus allows us to do is very easily change the topology. So we can analyze how this crack begins to grow and grow and grow. And so we've taken this idea and we've done a simulation where we started with a single face that is cracked, and then using a deterministic process, we can go one by one and continue to crack this until we've completely severed our two halves of our geometry. And we can all do that. We can do this without having to remesh. We can do this without significant modification of our system matrix. If we're dealing with a one field formulation, we only need to change 2 entries in our global system matrix every time that we introduce a new crack face. And so this was based on a very naive and simplistic criterion for propagating the crack. We basically determined a new crack face based on the maximum flux. But what we could do is we could go face by face, and the figure on the left is actually a series of points as we've propagated a single crack face all the way to the point where the block becomes completely severed. And so we were able to look at effective conductivity of our block as this crack face propagated. We also used the stochastic cracking process, and here it looks a little, the figure looks a little bit wonky because it's actually 100 different Monte Carlo paths that we've looked at, and we can see around 0.45 there were some paths that all of a sudden found the magic face to completely sever the block. So we have some that jumped down to 0 a little bit earlier than others. But this is a way that even though we started with a continuum idea, because of the discrete nature of our implementation, we can very easily introduce discontinuities into our simulations. So here is another example where, again, we started with a continuum idea, but because we're dealing with a fundamentally discrete description of the physics, we can, in this case, we've applied Ohm's law, which has a very similar form to the microstructure of a copper alloy. So we had EBSD data in 2D for a copper alloy, and we wanted to apply Ohm's law to it. Now, the unique thing that we were able to do here is we were able to define different resistivities, different resistances within a grain and within the boundary between grains. And again, it was perhaps a little bit of a naive approximation, but we fixed those resistances to misorientation angles between adjacent grains. And in that way, we were able to look at the heterogeneity of the electrical diffusion through this sample. So if you looked at the charge distribution through the whole sample, you would see a relatively, it looks like a smooth gradient. There are some spatial variation, but it's much more obvious when we look at the gradient, when we look at the current in our sample, and we can see a lot of spatial variation as we've taken into account these different misorientation angles as we've propagated charge through this specimen. And so the idea here is that as we can develop more intricate models of how things like misorientation angle or disclinations affect our charge transport through our specimen, we can look at different ways of processing our material and how that will affect things like its electrical properties. And then we'd also eventually like to look at its mechanical properties and the conjunction of the two, how they relate to one another. Okay, so this was a basic elliptical problem that we were able to solve using this process. But we also want to solve mechanical problems. And so here we're going to look specifically at linear elasticity. But as we saw in the previous examples, you can well imagine that even though we're describing linear elasticity, it's locally linear elasticity. So we can get geometric nonlinearity, we can get heterogeneity as we vary our material properties from one cell to another. And so we can actually build up much more complex models, even though we're starting with something as simple as linear elasticity. And while for our initial formulation, we studied linear elasticity, we're also working on finite strain theories and looking ahead to how we can model things like plasticity and fracture and more interesting things at a larger scale. So here, the work that we've done is based on a seminal paper by Dr. Arash Yavari from the mid-2000s, who proposed a discrete theory of elasticity, but wasn't able to completely introduce a constitutive law, which is pretty important. And so our major contribution here is eventually how we introduce our constitutive law and come up with a functional theory, discrete theory of linear elasticity, and can apply that to a number of different problems. So here we're going to start with our displacements as a primal zero cochain. So it's pretty easy to see the relationship between a continuum theory and our discrete theory. If we have displacements at nodes in our continuum, we also have displacements on our zero cochain, which would be defined at nodes. So that's why we have the zero flat operator applied to a vector field here. But when we actually implement this and go through it, we're going to use it as a zero cochain. We then want to define a discrete displacement gradient, which is a primal one cochain. And we can do this by applying our discrete exterior derivative to our displacements, our displacement zero cochain. So here, when we apply the discrete exterior derivative, it actually gives us a displacement difference. But remember that properties are intrinsically linked to their geometry. So we interpret it as a displacement gradient where the gradient is intrinsically tied to the length of the edge between the two zero cells. Using our musical isomorphisms, we can now relate this displacement gradient back to a continuous strain tensor, a continuous strain tensor field, and a continuous strain continuum stress tensor field if we want to. Again, we're interested in working in our discrete complex, but as we develop these methods, we want to be able to relate it to things that people are familiar with. So we have our continuous approximation that we can extract through these musical isomorphisms. So again, we're interested in what's happening in our discrete complex. Oh, one thing to highlight is when we do this mapping back to our continuous fields, then we have a permutation matrix between the vector representation of our displacement gradient and our stress and strain tensor. But when we move to our discrete, we have a discrete strain that's evaluated as a primal 1 cochain, and our discrete stress that is a dual 2 cochain. And so we do this mapping with through musical isomorphisms as well as a discrete Hodge star. So as we did with the diffusion problem, we want to include our material properties into our Hodge star so that we can have a constitutive relationship between our primal 1 cochains and our dual 2 cochains, where the material properties are accounted for in that mapping. And so we were able to define a non-local material Hodge star between our discrete displacement gradient and our discrete stress. Finally, applying a discrete approximation or a discrete mimic of divergence, we can come up with our conservation of linear momentum. So now we have our traditional linear elasticity equation, but defined on our discrete complexes. The final piece is to be able to impose, oh, right. So before we impose boundary conditions, I just wanted to highlight here that we can eliminate, at least partially eliminate, the use of discrete musical isomorphisms and get closer to a formulation that's entirely away from continuous fields by considering our permutation matrix. And every time that we see an identity in our permutation matrix, we can essentially eliminate our flat and sharp musical isomorphisms, because at a continuous level, they should at least be inverses of each other. And so we can eliminate that. And we're continuing to work towards formulations that are independent of these musical isomorphisms, even in our discrete Hodge stars. So as I was saying, we also need to impose boundary conditions. The way that we do that is through a closure of our geometry. So here we have a 2D example of a simplicial complex and its dual Voronoi shown in blue. So the primal is in red and the dual is in blue. And what you'll notice is at the boundary of our complex, the dual cells are not closed. So there's no edges that are closing the cell. And so this is a missing piece of information that we need in our dual complex to close our geometry and to finally close our divergence in those cells, which is a natural way for us to impose Neumann boundary conditions or force boundary, traction boundary conditions, right? So we can define our stresses along these incomplete edges, and we can then add them here, our T0S, as a closure to our final linear elasticity or conservation of linear momentum equation. Okay, if you're interested, we can go into more details about how we did that, but we'll leave it there for now and look at some of the problems that we were able to solve using this formulation. So I will say that, I'll be honest, that to date, we've only solved it with homogeneous material properties, but this gives us confidence that we're able to recover the same properties of our continuum approximations, and we're working towards, we've decided to focus on finite strain theories and modeling plasticity rather than looking at examples with inhomogeneity or discontinuities, partly because we need references for this so that we know how well that our methods are performing. But that's something that we're looking into in the future. So here, this is predominantly using homogeneous material properties. So here we're looking at the compression of a circular cylinder. So in this case, we only have a single normal stress in the vertical direction. And we've looked at Poisson's ratios from minus 0.95 up to 0.45, and we can get closer to the bounds if we want to. We just needed to pick a finite number of points to evaluate our theorem at. And we can see that whether we have a few hundred elements defining our circular cylinder or tens of thousands of elements defining our circular cylinder, we recover the analytic solution to within a very high degree of accuracy. We also looked at twist of a circular cylinder. So looking at a similar geometry as we had before, but now twisting the cylinder instead of compressing it. In this case, we're going to have a shear stress. So here we're looking at displacements, and we can evaluate the displacements through the radius of our circular cylinder very accurately. And then we can also look at the axial azimuthal shear stress components in our circular cylinder. And we see here that there is a little bit more of a spread. And this is a function of the refinement in our mesh. So if we have smaller cells, this is more accurate. If we have larger cells, it's less accurate. And this is because we are mapping from our discrete structure, and we're approximating a continuum idea at discrete locations. And this is a non-local process. So it makes sense that this is a function of our cell size, that as we approximate these continuum ideas from non-local data, that there is going to be some variation, and it's going to be a function of cell size. The reason why there's a gap towards the outer radius of our cells, or outer radius of our cylinder in this case, is just because of the nodal location where we evaluated it. We always had a nodal location on the boundary of our circular cylinder, meaning that for a finite size cell, there is a minimum distance away from the radius where our first interior node will be. And that's why there's this gap. So you get a sense of what the size of the cells are that we're dealing with in this case relative to the radius. We also looked at a case where we had bending. So this was the bending of a cantilever beam. Here we're showing for, again, a range of Poisson's ratio, the deflection of the beam for a prescribed tip deflection. And when we submitted our paper, the reviewer said, you can't do that. You can't prescribe a deflection and then look at the displacement along the center line, which we've done here. You need to prescribe a force at the tip and then look at the displacement. So we've done both. We've applied a displacement at the tip and look at the deflection along the length of the beam, and we've also applied a force. And when we apply a displacement, we get excellent results as shown here. When we apply a force, we get excellent results within maybe plus or minus 3, plus or minus 4 of a Poisson's ratio of 0. So that would be plus 3 and minus 3. As we go more negative, what we get is a natural stiffening of the beam, which is a phenomena that has been observed in real auxilic beams, that as we lower the Poisson's ratio further and further and further, there's a natural stiffening of the beam. And so I don't have the results to show you here, but we actually match very well with other results in the literature as the rate of stiffening as we lower our Poisson's ratio. So it's really nice that while we can get the one-dimensional result if we prescribe a displacement, when we actually take into account three-dimensional effects, then we're recovering the expected behavior as it moves away from this one-dimensional result with this natural stiffening. We've also looked at the Kirsch problem, which is basically a simplification of having an infinite medium with a spherical hole at the center and applying a tension through that medium, and looking at the stress along the radial direction out from that spherical hole. So here we're only modeling 1/8 of the geometry and applying symmetry boundary conditions. We're applying a tension, and we have an analytic solution for the normal stress along the radial direction from our spherical hole. And we can see that in this problem where we have a number of different stress components and shear stress components acting, that we do an excellent job of recovering the analytic solution. So this gives us confidence that we can model elastic problems, at least with homogeneous material properties, and gives us constant confidence that we can now start looking at discontinuous media and heterogeneous media as well. So all of the problems that I've presented to you so far have been solved on a laptop computer. These are all problems that we can solve on a high-spec workstation laptop computer. But ultimately, we want to take these relatively small model problems and we want to extend it to larger and larger scales towards engineering scales. And so we developed a software library, a parallelized software library that implements discrete exterior calculus so that we can extend these simulations to massively parallel computers or high performance computers, supercomputers. So we developed a library which we called Paragems, Parallel Geometric Mechanics of Solids. It's an open source library. You can go download the source code from Bitbucket if you want. It's written in modern Fortran 90 and uses MPI for parallelization. We've integrated compatibility with triangle and TET-gen mesh generation. And one of our aspirations is also to introduce compatibility with tools like Nepper, which gives us microstructure generation. The way that we've developed the software is we have essentially developed a math library on which we developed a number of mini applications to solve different problems. So whether that's a thermal problem, an electrical problem, an elastic problem, whatever problem that we want to solve, we'll develop a mini application based on this library. Finally, when we have the resulting system of equations, we then use the well-known PETSI library for solving those system of equations. And we have output in BTK format so that you can analyze it in tools like ParaView. So behind this description here is a microstructure that we've generated and brought into the library, and we solved a diffusion problem on. In the top right, we also have the scaling of this library. So we've analyzed the scaling from about 32 cores up to just over 1,000 cores. And we can see that especially on larger meshes that we get excellent scaling on 1,000 cores. So I believe that the largest problem here is about 20 million cells. And it's a two or mixed formulation problem that we're solving, and we get excellent scaling. But this wasn't good enough for us. We wanted to solve even larger problems. And so we looked to other tools that we could couple with our library to extend the performance. And the library we turned to is a finite element library called Parafem. It's also an open source library that is available online. It is also written in modern Fortran 90 and uses MPI for parallelization. It's a very convenient software library to use, as there's already many different mini applications that have been developed using this library for diverse physical problems, from elasticity, plasticity, fluid problems, eigenvalue problems, vibration, all kinds of different problems. So if we can integrate our DEC library into this finite element library, it opens up a whole realm of possibilities for the type of problems that we can solve. It's also being shown to solve problems with over 1 billion degrees of freedom on tens of thousands of processors. And so this is really the property of the software that we want to leverage. It also opens the door to interfaces with other software libraries for doing multi-physics simulation. And this is also a software library that has a textbook associated with it. So it's a tool that's used in teaching, in research, used for collaboration. And so it's a very powerful tool that we want to integrate our library with. And so what we did is, rather than coupling the two libraries at a large scale, what we realized is that both software libraries require input. Both software libraries require initialization. Both software libraries end up requiring to solve a linear or nonlinear system of equations and to have an output. And so our idea was that we would take the framework of the finite element library, and we would introduce DEC as a mathematical option for describing our properties, our problem, sorry. And so we have this really integrated software at the end when we couple these two software libraries. And it even opens the door that if we want to do multi-scale modeling using discrete exterior calculus for you know, a subscale process, if we want to model fracture or something locally in one area of our mesh, and then use finite elements for a more macroscopic or continuum analysis throughout the rest of our domain. We have an easy and natural way to introduce that coupling. So here is a code snippet from one of the mini applications in Parafem, which defines the mathematical matrix for the finite elements. It's the system matrix that is used by integrating the finite elements. So what we did is we took this small snippet of code and we introduced our discrete exterior calculus. So we were able to use the same loop through the finite elements, but rather than treating them as finite elements, we treated them as elements in our discrete exterior calculus, as cells in our discrete exterior calculus. So we did some conversions so that we could deal with both hexes, hexahedra, and tetrahedra, which would be simplex. We introduced the required calculations to compute the topology and the geometry of our cells, and then populating the matrix in a similar way that you would do with integrating the finite elements, but now we're introducing the coefficients associated with our discrete exterior calculus formulation. So this is a very small part of the mini application, a small change in the overall formulation, but now we're able to integrate our discrete exterior calculus. And you can see that this really opens up natural ways of integrating and coupling finite elements with discrete exterior calculus. So we then looked specifically at our diffusion problem again, both a continuous diffusion problem and a discontinuous diffusion problem. We're also working on implementing our elasticity. It's not quite complete, but we're working on it. And here, what we're showing is that we can now extend our excellent scaling up well over 10,000 processors. Here we get excellent scaling up to 16,000 processors for a mesh that has 200 million elements. So here I've broken it down between the construction of the system matrix and the final solution, which is, what is the solution? It uses a conjugate gradient, a preconditioned conjugate gradient solution method. So here we have strong scaling and also weak scaling specifically for the construction of our system matrix, and then reasonable weak scaling for the solution as well. And what we expect is that as we move to larger and larger meshes, that we can extend this scaling performance to higher and higher core counts. So to give you some context, we were able to fit about 20 million cells on a single compute node. So that would be 128 processors on the particular system that we were using. And then, so that means that with 20 million cells on a compute node, when we go to 1,000 processors, we should be able to solve problems with about 200 million cells. And when we move to 12,800 and about 10,000 processors, we should be able to solve problems with about 2 billion cells. And then if you wanted to extend that further to 100,000 processors, theoretically, you could solve problems with about 20 billion cells. Now, there's a lot of issues when you try and solve problems that big on that many processors that we probably won't quite recognize that type of scaling. But that's the direction that we want to be moving, that we're solving problems with, you know, hundreds of millions, billions of cells to represent larger and larger problems. So kind of in conclusion, and looking ahead to the future, we've been able to look at some very basic problems using discrete exterior calculus, both diffusion problems and elasticity problems. But by using this discrete approach, we've actually been able to do some very interesting things looking at discontinuities, heterogeneities, and it gives us hope that we can do this also with mechanical problems. So we're continuing to develop our mechanical formulations so we can move away from needing to use musical isomorphisms completely. We're also looking at extensions to finite strain, to plasticity, looking ahead to fracture as well, and how we can do that. Looking at how we can look at how energy is distributed across our complex and how we can leverage that in these formulations. We're also looking at other discrete forms of exterior calculus. If you remember, I said discrete exterior calculus is only one discrete form of exterior calculus. So we're also looking at things like Foreman's combinatorial differential forms and to have more robust and feature-filled mathematical descriptions that we can use to define our mechanical properties. I'm also, one of the things that I'm passionate about is interactions between things and connections between things. So both like multi-physical interactions, but also interactions at the mathematical level. So how can we take these discrete formulations that we have and develop interfaces with known continuum approaches like finite elements, finite volumes, or a formulation that I worked on, generalized summation by parts operators, which are finite difference-based operators that have natural discontinuities in their formulation. And so can we combine these two ideas? Can we find trade-offs? Can we learn as we interface these technologies? Can we learn and transfer technology from generalized summation by parts into discrete exterior calculus, or from discrete exterior calculus into finite volumes? How can we learn from these different methods and how they interface to develop more robust mathematical formulations to better simulate and to have more efficient simulation of our physical or multi-physical problems? As I mentioned earlier, we're interested in doing simultaneous multi-dimensional problems. And so this was in a recent paper that we've submitted for publication, we did just that. So here, the idea was that we had a relatively non-conductive matrix, and we wanted to gradually add graphene nanoplatelets or carbon nanotubes to see what would be a critical percentage of graphene nanoplatelets or graphene carbene nanotubes that we would need to include in our matrix to get a jump in the electrical conductivity of our overall specimen. And so this is just a brief summary of the results. This was done with Foreman's combinatorial differential forms rather than discrete exterior calculus explicitly, which is why I didn't include it in the main part of the talk, but we're moving in that direction. So we have a three-dimensional specimen that we're analyzing, but we have one and two-dimensional processes, the electrical properties that we're looking at propagating through this. And we're also looking at this in terms of looking at porous materials and gas diffusion or gas permeability, looking at thermal diffusion in porous material and different things like that. There's interest in hydrogen diffusion in different metals and things like that. I'm also interested in coming here to KFUPM in corrosion and how we can use these ideas to model the propagation and evolution of corrosion, or looking at how fluids diffuse through concrete and things like that. So lots of opportunities that we're looking forward to in the future. Again, I'm very interested in multi-scale, multi-physics description, and using all of these different analytical, computational tools, mathematical tools to eventually start looking at life cycle analysis of high-value infrastructure, to look at resilience as systems evolve in harsh environments or undergo extreme events. For example, if there's an earthquake, or whether there's a failure somewhere else in the system and it creates shocks elsewhere in the system, and how can we evaluate the performance of these systems as they evolve through their life cycle, and to sustain natural aging, damage, as there's failure in one component, how that affects the rest of the system, and so on and so forth. And so that's kind of comes back to where we started this talk, and my overall vision or ambition in this research and the development of these mathematical and computational tools. And so that's where I'll end the talk for today. Thank you very much for your attention. Unfortunately, I can't see you, so I will assume that you all paid excellent attention, and I would be happy to entertain any questions if you have any.
Thank you very much, Dr. Pieter Boom, for an excellent presentation and a very interesting one, and showing the new directions in which IRC-CBM can also conduct research. So we have questions coming in. So first question is from Dr. Faisal Mukhtar from Civil Engineering Department. Good job, Dr. Boom. Please, can you comment about the stability of the generated system of equations which are generated using this approach? The matrix conditioning, convergence, rate, etc. And the second question, is the system a sparse symmetric system?
Yes, those are excellent questions. I will answer the second question first. So yes, the implementation of all of these problems that I've shown are very sparse, and we have implemented them as symmetric systems. So that is definitely a possibility. We are using sparse symmetric solvers in both cases. The comment on conditioning, convergence rate. So matrix conditioning, this is a challenge and a very good question. And so it really depends on the geometry of your cells. So some of the issues that we've run into is, for example, if you start with an arbitrary simplicial complex and you compute the Voronoi dual, you can come across situations where you can have dual one cell, so dual edges, or dual two cells, faces that are zero or close to zero. And this can introduce poor conditioning into your system. So if it's absolutely zero, you can actually eliminate the primal edge and the dual two cell, basically remove that connection without destroying the physics that you're representing. So this is one possibility for overcoming this type of poor conditioning. But yeah, so the predominantly poor conditioning comes from the geometry, when we either get very small edges or very small faces. And so we're still developing ways of overcoming this. This, inshallah, will be improved using the Foreman's approach, because rather than looking at circumcentric duals, which tend to lead to this phenomena, we're dealing with barycentric duals. So it's less likely that we have these geometric singularities, if you will. In terms of convergence rate, there are people who are working on evaluating a convergence rate for these methods. So in this case, depending on what variable you're looking at, if you want to do a strict convergence study, you get either first or second order, which is a low order. But one of the things that we argue is that convergence rate doesn't really make sense, because we're trying to move away as best we can from these continuum ideas, where you want your finite differences to converge to a continuum solution. Whereas here, we're interested in how the discrete nature of the problem is influencing the solution. And as we want to solve larger and larger meshes, one of the penalties that we take is simplicity, which gives us lower convergence rate. However, integrating ideas from discontinuous finite elements or generalized summation by parts may be a way to realize higher order convergence rates, at least locally for these methods, even if we're still aiming towards these more discrete approximations. Hopefully that answers your question. I'm happy to answer any follow-up.
Dr. Faisal, do you have anything?
Yeah. Thank you, Dr. Boom. Yeah, very good answers I got there. But when I talk about the conditioning, if you, for example, look at the finite element, it has a constant condition number of about 0.5 on all problems, more or less. And then due to improvement, we go to extended finite element, where we see that in most cases, we are sacrificing the good conditioning number of finite element until maybe some more effort is put in the research. We usually sacrifice some conditioning. That's what I meant. So this method, does it have no specific condition number or?
That is a good question. I don't have an answer for you right now, but that's something that we could look into.
Okay. So Dr. Osta, do you have a question?
I don't have any question. Assalamu alaikum. Rather, I would like to thank you and to thank our distinguished speakers and all the attendees. It was really great pleasure to listen and to learn so much from this excellent topic. And I will take this opportunity to thank you on behalf of the IRCCBM. Hopefully, inshallah, will be our pleasure to invite you again, once again in the same subject. Thank you again. Thank you.
Thank you very much.
Thank you very much,
It's been a pleasure and an honor.
I see that there are no further questions, and we have about 1 hour and 40 minutes of this talk. And just one question in the end I'd like to ask is that what areas do you see in our IRCCBM where this approach, for example, in concrete, could work in a better way as compared to the finite element-based approach?
Yeah, that's a very good question. Thank you. Well, I mean, one of the things that I'm interested in is looking at concretes. So a concrete is a combination of a number of different things. You have a matrix, you have aggregates. These certainly aggregates have finite dimension, and I think this could be a very natural use of this approach to model those essentially composite systems, especially if we want to start looking at things like fracture and the evolution of fracture in these materials. Again, using this type of a discrete approach might provide some benefits, because having a fundamentally discrete description gives natural avenues for the cracks and things like that to propagate. Also, one example would be like fiber reinforced concrete or things like that, where you might have low dimensional structures within your three-dimensional volume, and wanting to analyze how you have an interaction between these low dimensional structures and the higher dimensional overall volume that you have, and how material mechanical properties or different multi-physical properties evolve on that. Something that you and I have discussed is looking at corrosion, and so looking at how different fluids diffuse through your concrete, for example, and then how you model the chemical reaction with your steel rebar or whatever it is, and then how that propagates back out from those initial sites through the concrete and change its mechanical performance and things like that. So those are a few ways that I've been thinking that we might be able to apply this modeling approach.
Thank you. That's a good area really to work on, and these young students and our postdocs who are here in this webinar would really start thinking and moving in that directions, and especially enhancing the modeling theme of IRCCBM. So if there are no further questions, then we have to close this seminar. And to close, first of all, I'll thank all the attendees, who were about 20 attendees who attended this webinar, from faculty and the students of the civil engineering department. I could see mostly. And thank you, Dr. Pieter Boom, for this excellent and very informative presentation. And hopefully this presentation and this webinar will lead to further collaboration between our center, the students, and yourself. And thank you, Dr. Osta, for this arranging and organizing this webinar, monthly webinar, and we will hopefully meet you in another webinar on another interesting topic next month. And what we are targeting next month is energy in the topic, where one of the grand challenges which IRCCBM is addressing is a grand challenge is that how we reduce the energy consumption in a building by 50%. And that grand challenge is being taken up by RCCBM in cooperation with the architectural engineering department. So hopefully we will have an interesting another webinar next month, and all graduate students, postdocs, and faculty members are invited to attend that seminar, which will be announced through KICS. Thank you very much. And that's it for today. Assalamu alaikum. And we will meet you next month, inshallah.
Thank you, everyone.